Well, good morning, team. Chemistry Coach coming at you, continuing our look at liquid properties. So we broke this up into two videos. Last one we did, what did we look at? We looked at viscosity, where I ate a little more honey than I planned on, motor oil, all that fun stuff. Surface tension, we looked at capillary action and mixed in with that, why a meniscus forms, concave or convex. So that we kind of crammed onto one video. So we made a second video here based on just So we're going to mix in several concepts here, all under evaporation, and I'll put boiling in there. Intro chemistry, we kind of treat, vaporization, evaporation, boiling kind of all is the same thing. Well, it's not technically correct, but usually good enough. So we're going to mix in the liquid property like molar heat of vaporization, how much energy it takes to, convert 1 mole of a liquid into a gas. So we'll look at how that's impacted by intermolecular forces. We're going to look at evaporation versus vaporization versus boiling and its dependency on temperature and pressure. There's a whole lot. So this gets a video in and of itself, and this will be the last liquid property we look at before we jump into solids, just so you can get a feel for the play of intermolecular forces and temperature on liquids and stuff. All right. So I'm pretty sure you all know at this point, if we're going from a liquid to a gas phase, right? Most of the time we'll call that vaporization, enthalpies of vaporization, etc. But technically, if you're below the boiling point, we will call that evaporation, where you're just peeling off the surface layer, molecules or atoms of liquid at the surface. You see, I'm in Southern California, it doesn't rain very much, like hardly ever, a couple times a year. But when it rains, you get little puddles outside, right? That puddle doesn't stay there forever, correct? It goes away. Well, have you ever walked or ridden your bike or something along the side of the road and seen a puddle of water boiling? No. So it never hit 100 degrees Celsius outside. That would be 212 degrees Fahrenheit. That would be a really bad day for everyone, wouldn't it, if it got that hot, even in sunny Southern California. So obviously, that puddle of water never boiled. That'd be insane. So it never is, but that means the liquid still went to the gas phase, even though the temperature never hit the boiling point. Welcome to evaporation, right? So what we're doing is peeling off that top layer of that puddle, exposing the next layer, exposing the next layer, right? So it peels off over time and eventually it goes away. Very temperature dependent. Very dependent on the rate of that evaporation based on how strong those liquid particles are attracted to each other. So let's take a look at it. Right? So if we have a liquid, usually it's a compound, right? Molecules, but you could have mercury or something where you have atoms. So you've got these particles of a liquid. You've got some at the surface, and you've got the rest in the bulk, right? What we call the bulk, and then the surface. Cool branch of chemistry called surface science. It's really neat. So you just look at the surface. Whole different world at the surface versus the bulk. So if those molecules or atoms of that liquid at the surface peel off, right? We call that evaporation. Well, how do they peel off? Because, like if it's water, they're hydrogen bonded to each other. The ones on the surface are hydrogen bonded to the ones below it, obviously, and then it's just air above. And the ones in the bulk are surrounded by, hydrogen bonded to all the water molecules around it. But how are they going to peel off below the boiling point? Well, remember, you've got thermal motion. These aren't static. They're not just sitting there. Those molecules are moving around, right? Moving around, vibrating, it's not like a gas, right? But you still have vibrations and things, and there can be a collision and transfer of energy. So not all, at whatever temperature you're at, not all those liquid particles are going to have the same kinetic energy. So depending on what the temperature is, you're going to have a certain amount of thermal energy providing kinetic energy for those liquid particles. And there's a certain percentage of them. Remember that bell curve when we looked at gases for gas kinetic energies and speeds? You get this bell curve because of collisions and transfer of kinetic energy. It is possible that one of these particles will pick up enough kinetic energy to overcome the intermolecular force strength. Remember, these are holding on to each other right here. But if this, let's take this one here in red, let's say that particular molecule of that liquid picks up enough kinetic energy due to collisions from surrounding liquid particles, if it picks up enough kinetic energy and it's greater than the intermolecular force strength holding that particle to the other ones, it can peel off into the gas phase. Right? So poof, off it goes. And that actually takes some energy away from the liquid. Right? So the liquid actually is cooler. That's what happens if you ever taken a shower or get out of a pool or the ocean and you get outside and the water starts evaporating. You're like, oh, that's so cold, right? Or in lab, you get some, ethanol or isopropyl alcohol at home on your hand and it evaporates. I'll tell you, it feels cold because what it's doing is that kinetic energy. This is usually a higher energy than the other one, so the kinetic energy of the rest of it drops a little bit, right? It feels cold. It's taking energy away. That's why when you're exercising and you start sweating and that sweat evaporates, it cools you off. It's kind of important, but that's a whole different ballgame. I digress. So that's what evaporation is, right? And that can continue. Right, until if it's open to the atmosphere, that could continue until all the water molecules or whatever liquid it is are gone. So what I want to look at are these two factors here. The kinetic energy, which is based on the liquid temperature, so this is very heavily temperature dependent, and the intermolecular force strength of the liquid. Think about those factors. If the intermolecular force strength increases, will you get more particles into the gas phase or less? If the temperature is higher, will you get more into the gas phase or less? Think about that and predict it. And let's do it on the next page, next board. All right, we've got, did you predict the results of this? Hopefully pretty easily. So the two main factors involved in the evaporation rate, right? Intermolecular force strength. And we're going to measure that with a numerical value that you've seen before on the next board. So if the intermolecular forces are stronger, right, they're increasing, those molecules or atoms of liquid are held tighter together, which means fewer of the liquid molecules have enough kinetic energy to overcome that and pop into the gas phase and join the rest of the molecules in the atmosphere, right? So would you agree there'll be less evaporation occurring at whatever temperature you're at? But the stronger the intermolecular force is, the less evaporation will be occurring. So you'll have fewer particles in the gas phase. Simple. Or if we flip that on its head, the weaker the intermolecular force is, the easier it is to break them, right? So at a particular temperature, more liquid particles will have enough kinetic energy to overcome those intermolecular forces. Pop! Into the gas phase it goes. Evaporation occurs off of the surface. We call that a volatile liquid, right? So liquids with weak intermolecular forces tend to be more volatile, which means they evaporate more readily or more easily. So something with strong intermolecular forces, right, will be less volatile, right? Pretty simple. You'll see that term a lot in organic chemistry. Is that a volatile liquid or not? Or non-volatile, right? Really strong intermolecular forces. It could be non-volatile. Hardly any particles get in the gas phase. The other factor, of course, is temperature. So for a given liquid, if we start jacking up the temperature and increasing it, we're putting more thermal energy into the liquid, correct? Which spreads out due to collisions with the liquid particles, right? Which means the kinetic energy is increasing. So if we have a set intermolecular force strength and the kinetic energy is increasing because of increasing temperature, that means more liquid particles are going to have a higher kinetic energy necessary to break those intermolecular forces and pop off into the gas phase. So as temperature increases, right, kinetic energy liquid particles go up. That means more overcome the intermolecular force strength and the evaporation rate goes up. So at higher temperatures, you'll see those puddles of water disappear more quickly. So let's take a look at this numerical value we're going to use, molar heat of vaporization, that relates to the intermolecular force strength. I'll give you some values and talk about that. And then we'll talk about these little particles of what used to be in the liquid phase, now in the gas phase, when we talk about what's called vapor pressure, which you ran into briefly when we were talking about, I think in lab in first semester of general chemistry, we were collecting gases by displacing water. And that water was an impurity in the other gas. We had to use Dalton's law of partial pressures to correct for that. Well, that's a result of the evaporation of the water at some particular temperature. So let's take a look at that. All right, let's go back to thermochemistry way back in first semester general chemistry. Remember when we talked about phase changes, condensation, vaporization, all that kind of stuff. Well, we used the molar heat of vaporization or molar heat of condensation or molar heat of sublimation, etc., to represent the amount of energy it took, right, to convert 1 mole of a substance at one phase to 1 mole of that substance at another phase. So I highly recommend you go back and review any videos, lecture material, notes that you have way back in first semester general chemistry and thermochemistry at the types of calculations that we did for that. So delta H vaporization, of course, will be for liquid to gas conversions. And that's the numerical value we're going to use to represent the intermolecular force strength. I'm not going to make you predict them. I will always provide you these values. But does it make sense that as the intermolecular force strength increases, the molar heat of vaporization will be a higher value? It takes more energy to separate them, the liquids, into the gas phase. I hope that makes common sense. And therefore, the liquid will be less volatile. So liquids with high molar heats of vaporization, strong intermolecular forces, are less volatile. They'll have fewer particles in the gas phase at a given temperature versus liquids with smaller molar heats of vaporization. Right on? Just if you remember for water, depending who's teaching and what they do, a lot of them at the lower levels, I tend to assume that these are constant and independent of temperature. Not technically true. They're actually a little bit temperature dependent. So the molar heat of vaporization for liquid water at roughly room temperature is about 44.0 kilojoules per mole. So you'll commonly see that value. But at the boiling point, 100 degrees Celsius, it's about 40.7 kilojoules per mole, right? To 3 sig figs there. So obviously it's a little bit temperature dependent. I will provide you those values on exams and quizzes and homeworks and whatnot. And we can make a simplifying assumption here and assume that that's fairly constant over temperature ranges, right? So, we could say maybe, 10 to 40 degrees. Maybe that's not a real small temperature range, but somewhere in that range, we're probably okay using that value. If we're a little bit higher up, closer to the boiling point, we want to use this value. But if we're at a specific temperature, I will try to provide you the molar heat of vaporization value at that temperature. We good? But I'm not going to make you calculate this yet. All right. So let's move on. Let's get into this concept of vapor pressure, right? How do we represent the number of liquid particles that go into the gas phase at a particular temperature? And is there some equation that can actually represent that as well? Ooh, getting into some fun stuff later. Let's put a little twist on what we did before. So when we started this, I showed you that open container. It was open to the atmosphere, and then as these liquid particles on the surface evaporated, they just went off and joined the atmosphere, right? And then, like, for example, a whole puddle can disappear, or an open beaker of alcohol can disappear over time because the particles just go from the liquid phase to the gas phase, evaporate off, and whoop, disappear in the atmosphere. But what if we sealed it? Oh, this changes everything. So what we're going to do, we're going to have a closed container. So now if a particle evaporates, right, goes from the surface of the liquid to the gas, say we have enough thermal energy. So for, theoretical sake, let's say we start with just liquid, there's no vapor. Okay, and depending whatever the temperature is, higher the temperature, the more this will occur. The lower temperature, the less it will occur. But it'll occur at every temperature. A particular particle, let's put the ones in the liquid phase in blue and in the vapor phase in red. So it is possible one of these picks up enough kinetic energy to break the intermolecular forces and boop, goes into the gas phase, right? And maybe another one does, and maybe another one does, right? Obviously it'll be a lot more than 3, but can you see that the liquid layer the height of the surface will decrease over time? So we can't see the individual particles with our pathetic human eyeballs, but we would see over time, maybe we left for 10 minutes, came back, the liquid level will have dropped, even though we couldn't see the vapor. It'll be like, oh, where'd the liquid go? Well, if it's a sealed container, obviously it didn't go in the atmosphere, it must be here. It could go up, bonk into the top here, bonk around, so these particles in the gas phase are moving around. Would it make sense, though, that one of these gas particles could go boom, hit the top, and go bang, back in? Oh, my. So it's possible, I'll put that in purple, So evaporation are these arrows in red going from the liquid to the gas phase, right, or the vapor phase. But is it possible for one of these gas phase or particles in the gas, what we call the vapor, right, could strike the surface of the liquid, lock in the intermolecular forces, and then condense, right? But the evaporation rate would be higher than the condensation rate, so you'd still see the liquid level go down. But there should be a time when the evaporation rate equals the condensation rate. So boom. And once we hit that particular scenario where the number of liquid particles peeling off the surface into the gas phase equals the number of particles in the gas phase going into the liquid, then the liquid level will stay constant. We will see it drop, 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 and then stop. We're in a special place we're going to study a lot later called equilibrium, where the two opposing rate, condensation and evaporation rates, are opposite, but they're equal to each other. It's like 3 people leaving a room at the same time 3 other people enter the room. The number of people in the room doesn't change, even though it's in constant dynamic process. This is called dynamic equilibrium. So when those are equal to each other, we call that equilibrium. At equilibrium, dynamic equilibrium, would you agree there's going to be a certain number of particles in the gas phase, right? A constant number of particles in the gas phase. That, the pressure exerted by those particles in the gas phase, is your vapor pressure, or VP. And there's tables of this stuff, and it's obviously temperature dependent, right? So the pressure exerted by the particles in the gas phase, right, in the vapor, in equilibrium with a liquid in a closed container, is by definition the vapor pressure, right? So the pressure of these particles is the vapor pressure. So pressure of the gas phase particles right there is the vapor pressure. So let's take a look at how the vapor pressure depends on the intermolecular force strength of the particles of this particular substance, whatever it is, and the temperature, right? So see if you can predict it. Let's say we're at some constant temperature, right? And we've got 2 liquids, for example, one with weak intermolecular forces and one with strong intermolecular forces. Which would have the higher vapor pressure? Oh, and then let's flip that around and say we've got the same substance at a low temperature and a high temperature. In which scenario would the vapor pressure be higher? Predict that, and let's write that on the next board. Let's do it. Is this what you got, gang? So let's look at intermolecular force strength and temperature and its impact on the vapor pressure for a particular liquid, okay? So the higher the intermolecular force strength, the harder it is to separate them, right? Well, wouldn't that make sense that there'd be fewer particles in the gas phase if they're harder to separate? Which means it'd be a lower vapor pressure. So as intermolecular force strength of a liquid increases, the vapor pressure decreases, right? Fewer particles in the vapor. Let's take an example, right? Ammonia versus methane. So if you look at ammonia, right, it's got hydrogen bond. They're roughly the same mass, give or take. So London dispersion forces are pretty similar. But this has hydrogen bonding. It's a polar species with hydrogen bonding. Methane's a nonpolar species, right? So very much weaker intermolecular forces for methane. So it's easier to get methane and break its intermolecular forces, get into the gas phase. So if they're at the same temperature, they got the same kinetic energy, more methane particles will go into the gas phase than ammonia. So ammonia will have a higher molar heat of vaporization because of the stronger intermolecular forces. Methane will have the lower heat of vaporization, molar heat of vaporization. Good? Which means there'll be fewer particles in the gas phase for ammonia because it's harder to separate, and a lower vapor pressure. Methane has more particles in the gas phase, or the vapor, and has a higher vapor pressure. Pretty easy to do, right? Not too bad. And you can look up values for these. You can look up values for vapor pressure. We're going to look at vapor pressure pretty closely. We're going to actually graph some of this. We can look at how it changes over temperature and graph it. We love graphing. Now let's look at temperature. If we have the same species, so let's just take ammonia at like 25 degrees Celsius versus 55 degrees Celsius, or methane at 25 degrees Celsius versus 55 degrees Celsius. As you increase the temperature, you're increasing the kinetic energy, and so more molecules overcome the intermolecular forces and pop into the vapor, right? So vapor pressure does increase as temperature increases. And we can measure this in a lab, right? We could go set the temperature at 10 degrees Celsius, 20, 30, 40, and measure the vapor pressure using a manometer or something. And we could prove that the vapor pressure increases because there's more particles in the gas phase. We got it? Let's look at this trend. Yeah. All right, so we looked at the temperature dependence on the vapor pressure, right? Goes up, right? So we can measure that in the lab. So you probably remember this from last semester, hopefully, when we did the collecting a gas by water displacement. We had these vapor pressure tables, right? And this is for water. Happens to be in millimeters mercury, right? But you can see the data, right? This ranges from 0 degrees Celsius all the way up to 56. That's as high as this particular table went, but obviously as you get to higher temperatures, the vapor pressure increases. So at 56.0 degrees Celsius, you're at 123.9 millimeters mercury or torr. And if you're down at like roughly room temperature, so let's say 20.6, that's a cold day, you're at about 18.3. So we have proof here. This is what you would get if you went in the lab and tabulated this, right? You can do it. You can do experiments and do this. But people don't like reading tables that much. We like to plot things so you can just look at the graph. Yay! Right? So if we plotted this, I'm not going to sit here and do every data point, but if we plotted any liquid, right, and looked at its vapor pressure over a temperature range, you're going to see they all have a similar trend. It's not going to be a nice straight line, I'm sorry. So you're going to see a trend like this. Right? It's called a vapor pressure curve. So if we plot it over, the vapor pressure at different temperatures, you'll see it jump like that. Now, chemists don't like curved lines, right? We like straight lines, right? Because then we can get a y equals mx plus b from that. Trying to get a mathematical expression for this is not pleasant. Now, we could easily, instead of reading, if I gave you the temperature, you could just read the vapor pressure off a table. But if you don't have a table, we can just put all the data on a graph here, and then I could say, hey, if we're at this particular temperature, you could just go up, boop, 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 and over, boop, 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 sound effects optional. And you know what your vapor pressure is. Or you could say, hey, for a vapor pressure of a certain value, what temperature would it have to be? You go over, go down, and that's the temperature that would give you that particular vapor pressure. So you can read them pretty easily off of a plot like this, right? And in our homework, we're going to be doing a few plots where I'll give you some data, not that many data points, but you'll have to make some vapor pressure vapor pressure curves like this from a vapor pressure table, right? Chemists love to get that tabulated data into some kind of plot, right? Now, there's an interesting point I want to point out before we do the mathematical trends of this. There's a very special pressure, right? So do you remember at sea level what we defined? Right, so especially where we're on the coast over here in Southern California. At sea level, or roughly at sea level, pressure is 1 atmosphere. So if we look across here and go, dun, 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 and let's draw a line across, and I can do different liquids have different intermolecular forces, so the curve will look the same, it will just be shifted over, right? No big deal, but it's the same idea for every liquid. That 1 atmosphere, that pressure is a very special pressure, right? Because if you're evaporating a liquid at a lower temperature, you get more and more particles into the vapor phase, represented by the vapor pressure, right? We'll just do P instead of EP. But as you heat it up, that vapor pressure gets higher and higher and higher. You have more particles in the gas phase, right? Let's say we have an open container. What happens right there, my friends? When the vapor pressure of the gas particles above its liquid equals that of the surrounding atmosphere. Ooh, right? So you're going to boil some, top ramen or spaghetti or something. You're going to cook that up. You put a pot of water, out of your faucet, stick it in a pan, put it on the stove. you wait for a while, right? It doesn't boil immediately, does it? You're heating it up, heating it up. Now it's evaporating, right? Just put your hand over it. You're like, oh, ouch, right? Because those particles are peeling off the surface with a high kinetic energy and they bounce off your hand. You're like, ouch, that doesn't feel very good. You can calculate the energy change from that from last semester. Remember the Q equals N delta H VAP, right? So you can calculate the energetics of phase changes, Q equals MS delta T for things heating up and cooling down. So you could calculate, the energy being transferred to your hand, by the way. So you put that over a pot of hot water. It's not even boiling. It still hurts. But as the temperature goes up, it hurts more and more and more. Don't leave your hand there and test that. But we wait until it starts boiling, and it takes forever when you're watching it, right? But why does it boil after some particular amount of time? Because what's happening is you're heating it up, heating it up, heating up. The vapor pressure is increasing, increasing, increasing. And then all of a sudden, boom, when the vapor pressure above the liquid equals the surrounding atmospheric pressure, that's when boiling commences. That, my friends. And if it's at 1 atmosphere, we call that the normal boiling point. Right? That's called the normal boiling point. When we say boiling point, we usually mean or imply at 1 atmosphere or sea level, right? Pressure. So we're gonna on the next board, what I'm going to do is I'm going to define boiling and compare that to just evaporation. But just remember that key point: when the vapor pressure above that liquid equals the surrounding atmospheric pressure, it boils. But what if you're at a lower pressure? What if you're higher up on a mountain? Say your pressure's here. You heat it up, it's going to boil here. Do you see that? So if you're up on top of a mountain and it's lower, the surrounding atmospheric pressure is lower, you're going to boil at a different temperature. Do you see this? You may have known this already, but it turns out boiling points right? So that temperature you read at that point would be the normal boiling point. So you just see where you intersect at the line, and that's your normal boiling point. So if you're at a lower pressure, you're at a lower temperature. So boiling points are temperature dependent. So when somebody says, what's the boiling point of this liquid? Technically, that's a vague question. They should say, and they should give you a pressure. If they don't give you a pressure, you have to assume they mean 1 atmosphere, and they're saying, what's the normal boiling point? But we get tired of saying that. We just say boiling point. Just assume it's the normal boiling point, unless we're at some other pressure, and then we specify that, right? So let's define that on the next board, because I don't have space here, but you can see how we got that from the graph. When it heats up to that point. Let me write that down for you real quick. All right, let's get this written down here for you. So when boiling commences, remember, you're heating up a liquid, evaporation's occurring off the surface, you don't see any bubbles, it's just peeling off the surface, right? But when that vapor pressure is increasing, and once it equals, right? So when the vapor pressure of those gas particles leaving the liquid equal the surrounding atmospheric or barometric pressure, we measure atmospheric pressure with a barometer, right? The liquid begins to boil, right? So you see bubbles throughout the liquid. You've seen that many times. If you cook, hi, Beach, how you doing? Get my kitty cat. So when it's evaporating, you don't see any bubbles, right? But then you're watching your water, and all of a sudden, you start to see a little bit. Oh, put my top ramen or my spaghetti or my macaroni noodles in. Yay, it's boiling. So you start seeing bubbles all throughout it. Now, don't let this deceive you. When you start heating water, you might see little tiny bubbles almost immediately. That's just escaping air, right? Nitrogen, oxygen molecules, as we'll find out later, as you heat up liquid. Any gases dissolved in it become less soluble. So those first initial tiny ones are just escaped gases. But then you see nothing, and then all of a sudden you see these big bubbles starting from the bottom, right? Because it's hotter at the bottom. And what happens is you're starting to get that vaporization throughout the entire bulk of the liquid. And you tend to get more at the bottom because it's hotter down there. And so those gas particles form these little bubbles. And the vapor pressure inside that bubble is high enough where the pressure of the water, liquid water, can't collapse it. Right below that, any bubbles that try to form get collapsed because the vapor pressure is lower than the pressure of the water pushing against it. Right. But at this point, right, the vapor pressure in those bubbles, right, they're not going to collapse, so they rise up through the liquid and pop at the surface, and off they go, right? They're less dense, of course, that's why they rise. But that's what boiling is. Think of it as a special point of vaporization, right? So 2 definitions for you. Boiling point is when the vapor pressure above that liquid equals the surrounding atmospheric pressure or barometric pressure. Simple. And we saw that. You can see the vapor pressure curve, right? That goes up. If we define sea level and atmospheric pressure at sea level as exactly 1 atmosphere, 760 torr, when the vapor pressure equals that, we call that the normal boiling point. Again, that's typically what we're talking about, right? Right. And so on the next board, let's talk about what happens, as I mentioned, if you decrease the surrounding atmospheric pressure, things change a little bit. Ha ha ha. All right, so we're just going to write down what we saw when we looked at the vapor pressure curve. We proved this just looking at the graph. It was easier. But qualitatively, right, would you agree if you've ever climbed up a mountain or something, right, it gets harder to breathe? Well, it's because atmospheric pressure is decreasing. Right, as you go up, or if you're up in an airplane, they need to pressurize the cabin, or you guys might not survive the trip. Okay, I'm not a mountain climber, but I've had friends who've climbed up there, and you're like, ugh, you see those Mount Everest things where there's less atmospheric pressure, even though there's still 21% oxygen. 21% of a smaller number is less oxygen. So every breath you got less oxygen to move your muscles and have your brain operate. Right? Doesn't sound like fun to me, but hey, if you're into it, go for it. Well, follow the logic. If the surrounding atmospheric pressure is lower at a higher altitude, i.e. up in a mountain, wouldn't it make sense that the vapor pressure required to boil is also lower, right? So at sea level, it's 1 atmosphere. But if you're up on a mountain, and let's say it's 0.7 atmospheres, you only have to get the vapor pressure above your liquid up to 0.7 to boil, which requires a lower temperature, right? So I don't need as high a temperature to get to the lower vapor pressure, which equals the lower atmospheric pressure. Do you see the logic there? So boiling points decrease as the atmospheric pressure decreases, or the higher the altitude, the lower the boiling point. So if you ever climb a mountain and, or you hear about these Tibetan monks or something, and that they'll drink like boiling tea or something like that. I don't know if that's true. I've never been to Tibet, right? But if you're up on a mountain, would it make sense that water, which normally boils at 100 degrees Celsius at sea level or 1 atmosphere pressure, it's going to boil less than 100 degrees Celsius, right? If you're up on a mountain at a lower atmospheric pressure. So I don't know. We'll show you how to calculate that in the next video. But let's say the water boils at 80 degrees Celsius. Right, so you're heated up and it could boil, and maybe that's where you could drink it. You probably wouldn't take a cup of boiling water and go chug chug chug, and like, oh. But if you're up on top of a mountain, you understand chemistry, and you'd be like, well, that's actually not 100 degrees Celsius because we're at a lower atmospheric pressure because we're higher up in altitude. So I might be able to drink that boiling cup of water, right? Because it might be 75 or 80 degrees Celsius. It's pretty crazy, right? The drawback for that is if you've got boiling water and you're cooking, macaroni noodles or spaghetti noodles or hard boiling eggs or something, you're boiling them at a lower temperature. It's going to take longer. You ever hear that? It takes longer to hard boil an egg up on a mountain. Well, that's because it's boiling at a lower temperature. So I'm going to stop it here. So what I'm going to do is I'm going to take this and we'll look at it quantitatively, right? How can you predict what the boiling point is, or calculate the boiling point at some other pressure? Now you could read it. I showed you could read it directly off that vapor pressure curve. Just look over and see where it intersects that line. So that's easy to do. But if we don't have that graph, can we do it using an equation? So we're going to derive an equation called the Clausius-Clapeyron equation. I call it the CLAP. Right? And we can actually, I'm going to derive that for you on the next video, and we can actually calculate boiling points at any pressure, pressures at any temperature, all these fun stuff. So we'll hit that in the next video. Whew, this was a heavy one.